All right, still in section 4 of chapter 9, and we're gonna again develop another test. So we're still doing comparison tests. Right now, the previous comparison test was a direct comparison test, a term-by-term comparison test. We're now going to look at a scenario where the term-by-term comparison, it's one of those scenarios when you can't do a term-by-term comparison, or it's extremely cumbersome to do a term-by-term comparison. But the idea is the following. So another type of comparison that we can do. So let's start with what is needed, what conditions need to be met, and then we will proceed to what can we conclude. So again, the A sub n is the given series that you want to compare, and B sub n is the series that resembles A sub n. So that part is the same. Only now, instead of doing a term-by-term comparison, we're going to do what we call a limit comparison. So this is what we call the limit comparison test. Okay, right. So what do we need to do the limit comparison test? So first off, the given series has to be greater than 0, and the series that resembles the given series has to be greater than 0. So those two have to be met. In addition, so three things. The given series has to be greater than 0. The compared what we compare it to has to be greater than 0, and the limit as n goes to infinity of the quotient of those two has to equal L. Now, wait a minute. So what is the stipulations for L? Well, first off, L has to be finite. Well, that makes sense. And it has to be a positive number. Okay, so stay with me. So we'll know that A sub n, that'll be given to us. The B sub n is what we come up with. That it is it resembles A sub n, and we know whether it converges or diverges. That's why we would choose it. Then all we're going to do is take the quotient of the two and the limit as n goes to infinity, and we want to make sure that what we get back out is finite and positive. Now, if that can be done, then the limit comparison test is quite neat. It lets us say either both converge or both diverge. Okay, so the game is going to be as follows. Ready? Let's get started. So notice that I jump in. Remember, it just says show that it's going to simply say something like show that the following series below diverges, or show that it converges or diverges. I mean, either way, we're given the A sub n. We're given A sub n. We are not given a B sub n. We're going to come up with that in just a second. But what's really nice is we're told that A is greater than 0, B is greater than 0. So what we need to do now is, first let's come up with a B sub n, and then let's start to make sure it meets all the criteria to use the test, okay? So what should we compare it to? Well, this is, show that the general harmonic series below diverges. Well, this is a harmonic series, right? Because why? Because if we think about, well, let's actually write the general. Let's actually write the harmonic series, right? The harmonic series is just a special type of P series when P is equal to 1. So that series, that B sub n for that series is 1 over n, right? Because remember, it's n to the power of P, and this is the case where P is equal to 1, right? N to the power of 1. And this is a type of P series. which is what we call the harmonic series. And what we know about the harmonic series is that it is divergent, right? It diverges. Okay. So we've already established just from the given that if A and B are both positive numbers greater than 0, then 1 over AN plus B is always going to be greater than 0. And of course, 1 over N is always going to be greater than 0. So let's now, we can think about the criteria. I'm going to kind of go down the line. So the first criteria, right, was that A sub n is greater than 0. We can check that off. The second criteria was that B sub n is greater than 0. We can check that off. Now remember, they either both diverge or both converge. So since B sub n diverges, if we can meet this third criteria, then we can make a statement about A sub n. But let's see what the third criteria is. The third criteria is we got to take the quotient, and we're going to take the limit of that quotient as n goes to infinity of what? Of A sub n divided by B sub n. Now that, what comes out of that has to be a finite number that is positive. Okay, so that's our job right now. But as soon as we can check off that third criteria, then since they both diverge together or both converge together, then we will be able to make a statement about A sub n. So what's going to happen right now? Well, I'm going to be plugging in for A sub n. I'm going to be plugging in for B sub n. Let's go ahead and rewrite that. So that gives me the limit as n goes to infinity of 1 over AN plus B divided by 1 over N. Okay, so maybe you're thinking L'Hopital, maybe you're thinking some other type of algebraic technique, because right now I'm not getting any information about the limit, because if I'm just getting information that's 0 over 0 actually. So what I'm going to do is, in this particular case, you can rewrite this well, let's see, how do we want to do this? Well, but I'll tell you what, first off, you might want to go ahead and get rid of this complex fraction. Let's see if this, I'm going to work down here a little bit. So we can write this as 1 over AN plus B divided by 1 over N, which we can rewrite as 1 over AN plus B times N over 1, right? So we don't have to have this complex fraction. So that allows me to rewrite this as N over AN plus B. Let's see if that's any more helpful. So I'm going to take that and bring it here. So that's equal to the limit. Still haven't taken our limit, as n is going to infinity. But now it's just N over AN plus B. Okay. Now here, this is still not helpful because I'm still getting this indeterminate form of, now it will be infinity over infinity. So at this stage, there's an algebraic technique that you can use. You can divide the top and the bottom of this fraction by n. So let me rewrite that so you'll see it. So what's going to happen is I got the limit as n goes to infinity. And I'm going to tell you right here what I'm going to do. I'm going to divide right, the numerator and the denominator, by n. Now let's see what that looks like. So let's start with the numerator. If I divide the numerator by n, it's n over n. And that means I would also have to divide out the denominator by n. Okay, so now let's see what that looks like after we simplify it. So now it's the limit with n going to infinity. And we have 1 over, and that just ends up being a plus b over n. Now that's perfect. That's perfect. So now let's go ahead and take the limit as n goes to infinity. All right, well, as n goes to infinity does not affect the 1 because there is no n in the numerator at all. N approaching infinity does not affect a. And of course, b over n as n goes to infinity would just be 0. So we end up with 1 over a. That is our limit. Right, so our limit is 1 divided by a. Now, remember what had to be, remember the limit had to be finite, and it had to be positive. So as long as, let's start with the fact that a is greater than 0, so a is automatically going to be a positive number. So in this case, what we've met all of the criteria we need. And now that you've established that all 3 criteria have been met, then we get to use the limit comparison test. And what does the limit comparison test tell us? That tells us that if b sub n diverges, then a sub n diverges. So in this case, by theorem, what is that? That 913, I guess? Yep. By theorem 913, by the limit comparison test, a sub n what? Diverges. All right. So that's 9.4. These are just, for the most part, these tests are not bad. You're going to have to practice them a little bit, but you have the basics, you have the theory. Just you'll need to jump into the homework so that you can practice, because what it really comes down to is practicing finding a term that you're going to use as your comparison, right? You need to practice finding a b sub n. But other than that, you now know how to apply 2 different tests. See you in the next video.